So, greetings and welcome back to our series to understand linear algebra for AI and ML concepts by using a very problem based approach. So, what that means is we basically solve two problems practically and then tie the whole concepts to existing AI and ML machine learning, concepts. So while you watch this video, try and understand the flow. You might not get everything in one go, but surely you will get the hang of it. We just have the approach of a practice based, be practical, do a lot of problems, and yeah, I recommend you getting the book by Sheldon Axler. It's called Linear Algebra um, Done Right. So it's very, very good and can, give you a deeper understanding, especially if this is an industry that you're curious about getting into and want to have a firm foothold. We just have a recap in our first episode, which you can, if you haven't checked it out, you should. We talked about associativity, some of the fundamental um, concepts in matrices, just associativity and how vectors interact. This video series is good when you already have some fundamental understanding. So I would suggest if you are just starting out or you find this a bit advanced, you can go to the YouTube series Three Blue, I think Three Blue, One Brown, something of the sort. I'll put the link in the description for anybody who asks. I can comment. So if you can watch that first, you can come back and you can get a bit deeper with it. But even for the casual person watching, you can definitely get a thing or two. So in the class before, we learned about associativity and did some practical examples. And again, we did a summary of real life applications where associativity is, holds water, and how what kind of where it places itself within the AI infrastructure when you're dealing with neural networks and just training different models. Who should watch this? This is great for CS undergrads, computer science, any IT related courses that are dealing with AI. Anybody who wants to actually get hands on, like get under the hood of AI and machine learning. This is good to just know and have an idea of, because as you continue to become a more practical developer of such systems, it's important to understand what goes on, and this involves just understanding mathematics. Yeah, hobbies too. Anybody who's just curious, this might help to get you closer to your goals. Today's class is around vector spaces. We're going to do some worked examples. As is our custom, we have a very practice-based approach. And our first problem, we have an equation that we need to prove. So to prove, this is basically an operation that requires us to understand some of the fundamental concepts. So just if again, why I say you need to have a bit of a grounding, you need to understand what is, if you are recalling different definitions. So what would be an additive inverse in this concept? We're just going to discuss. So how do you so we need to recall the definition of an additive inverse. So for any vector, the additive inverse, negative v, is defined as the unique vector that satisfies the equation below. V plus negative V equals 0. So, I mean, if you think about it intuitively, it's kind of obvious. So the additive inverse, so literally the negative of that number that makes it a 0. Okay, so if it's V plus negative V, you get a 0. You can already see there's an element here we're talking of reversibility, which will be clear as we go on. Where 0 is the 0 vector. Step 2, consider the additive inverse of this negative V. So we want to show that the negative of negative V is V. To do so, it suffices to show that V is the additive inverse of negative V. That is, we need to check for the equation below, whether it holds, whether it's true. And if you think intuitively, it kind of makes sense. Addition in a vector space is commutative. So hence the equation below that, negative V plus V is equal to V plus negative V. So whichever way you put the the way you organize the digits, it's still going to give you the same result. So it's commutative. So from the definition of an additive inverse, which is V plus negative V, we can therefore prove the initial equation. Intuitively, you can see we've basically come to the conclusion. So since V satisfies the defining property of being the additive inverse of negative V, the additive inverses are unique. And we have negative, the negative of negative V is V. Yes, I think by now it might seem quite obvious. So why should you even care about this math problem in the first place? Why should it matter? So, I mean, for like if you had already understood this, you're probably wondering, yeah, so get to the point. You see, when we talk about applications of such problems, they do have now their applications in their practical applications in artificial intelligence and machine learning. So when we start by like a gradient based learning, which is the first application. So when you train neural networks, we update model parameters using gradients, vectors that point in the direction of the steepest ascent of a loss function. So we have parameters and as below. So sometimes we have to reverse the gradient for adversarial examples, gradient ascent, or reinforcement learning policy. So we have to go back to where we started just to ensure that whether our forecast is correct, So the rule negative the negative of negative V is V ensures directional consistency. So if we reverse a reverse, we go back to the original optimization direction. It guarantees stable and reversible transformations in vector-based computations. So like you have an element of you can go back to where you started, and you can see the expansion of data being very very consistent. Okay, so we have symmetry in vector spaces. So in machine learning embeddings such as word vectors, image features, latent vectors, in autoencoders, they live in vector spaces. Operations like negation, the negative V, correspond to the opposite meanings or direction in a feature space. So if you've watched the videos from 3 Blue, 1 Brown, which they have a series also that explains the fundamentals a bit more in detail than I will do here. So they kind of visualize a lot of the transformations. So once you understand that those transformations and the vector points represent real life situations, data that you're trying to work with, now you can understand where exactly the directional movement when you represent them in in dimension, in terms of dimensions, in that kind of 3D, 2D, 4D space using vectors. So V, a concept or a feature direction. Negative V is the opposite concept. So the negative of negative V equals V ensures that the opposite of the opposite brings you back. So this is very crucial in for geometrical consistency, as I was saying earlier, in embedding the spaces. So for example, in word embeddings, if V represents male, then negative V might represent female along a gender axis. So ensuring negative of negative V equals V maintains symmetry and interpretability. So if, I know, pretty simple, right? So V represents male, negative V represents female. So the negative of negative V is male again. So when you're using a computer to, or using processing power to kind of represent problems as vectors, we can now, you can understand sort of the processes now of computing that go behind it and make a lot of these things possible. So some other applications of this problem are practically linear transformations and autoencoders. So when dealing with autoencoders, PCA or transformer projections, linearity is assumed. So we have this the T there being represented. So hence, the negative of negative V ensures that double inversion or reprojection leads back to the same point. This property is used implicitly in ensuring lossless reconstruction and in convertible mappings in normalizing flows. We also have reversible computations. So in advanced architectures like invertible neural networks or reversible residual layers, each transformation must be mathematically invertible. So the idea that the negative of negative V is V ensures that operations that undo and undo truly return to the original, a property that supports energy conservation, backward passes, and memory efficient training, which we will talk about in future classes. We also have adversarial training. So in adversarial machine learning, we often perturb input vectors. We have an equation there. If we negate the perturbation twice, we must end up where we started. So again, repetitively getting the point here. The rule ensures mathematical consistency when flipping adversarial directions. Linearity, okay. So we have a second problem. Hope you got it until there. Our second problem is a bit more in depth, but around the same concept. But show that in the definition of a vector space, 1.19, this is a problem from the Axler book. You can get it in exercise 1B. The additive inverse condition can be replaced with the condition that 0v equals 0 for all v in this particular vector. So here the 0 on the left side is the number 0 and the 0 on the right side is the additive identity of v. The phrase a condition can be replaced in a definition means that the collection of objects satisfying the definition is unchanged if the original condition is replaced with a new condition. Yeah, so maybe you might need to read that twice to just get it, but we're gonna go into how to solve it because it's also quite simple. Just don't be taken away by the jargon. Let's go step by step carefully. We are asked to show that in the definition of a vector space, we can replace the usual additive inverse axiom. Every vector has an additive inverse with the conditions. So 0v equals 0 for all in this vector. So here on the 0 on the left is the scalar 0, and the 0 on the right is the additive identity in the vector space. The goal here is to show that if we assume all other vector space axiom except the additive inverse axiom, and instead assume that 0v equals 0 for all of this, then the existence of the additive inverses can be derived. That is, from 0v equals 0, we should be able to prove that for each v in this vector, there exists a vector w such that v plus w equals 0. You get, from even the first equation, we had to get 0 as, the addition of the additive inverse plus that vector would be equal to a 0. So just helping us to derive an equation that we will solve. So we recall the basic axioms. We are allowed to assume the following: distributivity of scalar multiplication as shown below, a plus b in being multiplied by v equals av plus bv. So then there's associativity of vector addition, which we have done in the previous video, existence of additive identity 0, and then the scalar identity 1v equals v, and then other standard axioms except additive inverses. So lots of jargon, but hang on with me, okay? How to solve this? So you derive the additive inverse from the new condition. We want to show that negative 1 by v multiplied by v serves as the additive inverse of v. So let's check this one. So v plus negative 1v, it should be equal to 0, right? So we know we use the distributive property, and therefore once you solve it out, we basically we've just expanded a very simple equation to get 0 at the end. And then just to get back to to conclude this, we have found the vector negative 1v such that v plus negative 1 into v is equals to 0. Therefore, each vector has an additive inverse, namely negative v. Negative 1, multiplied by v. This shows that the additive inverse axiom can be derived from the condition 0v equals 0. Hence, the additive inverse condition in the definition of a vector space can be replaced by the condition 0v equals 0 for all vectors in that space, for all vectors v in that space. Keep in mind, intuitively, 0v equals 0 ensures a scalar 0 and annihilates all vectors. This is strong enough when combined with distributivity to produce the negation property automatically. Again, why should you care about such problems and such simple expansion of equations that are seemingly a bit obvious? So in AI and machine learning, we have practical examples such that number one, they ensure stable 0 operations in computations. So in neural networks, data, weights, and activations are vectors. During forward or backward passes, you often encounter operations like the one below. The rule 0v equals 0 ensures that when a feature or weight is zeroed, like through dropout or masking or pruning, it contributes nothing to the output. No phantom noise or undefined states. If this didn't hold, your model could invent signals, and out of zeros, breaking the learning stability. Number two, there's a lot of consistency in linear transformation. So most machine learning layers, such as dense, convolutional, attention, are linear transformations. So y equals to wx plus b. So if x is 0, we expect y to be equal to b. That relies on this particular concept, which is the same as what we've just proven. So without that property, empty input vectors wouldn't map predictably, ruining the linearity assumption used in backpropagation and optimization. Like it would cease to be a straight line, which doesn't help us in these situations. So number 3, it guarantees valid vector space behavior and embeddings. So embeddings such as word to vec, but image embeddings, they live in vector spaces. If you scale embeddings by scalars, e.g. in attention scores, normalization factors, this property ensures that if the scalar is 0, the embedding becomes a 0 vector, meaning no contribution to meaning. This keeps vector arithmetic interpretable and allows weight combinations to behave geometrically. So in attention, shown by the equation below, if some attention score 0 equals to A equals to the 0, then that token contributes nothing. Exactly, which is the law 0v equals 0 at work. Just to keep the linearity, we have sparse data dropout. Many machine learning models rely on sparse vectors, lots of zeros. So bag of words, sparse embeddings, think LU activations, which have zeros, dropout masks. So the fact that 0v equals 0 ensures that dropping or zeroing an element removes the influence completely, which is what allows sparsity to be computationally meaningful. So I think you can start to get the hang of why these zeros, something self-explanatory, should be there. Excuse my ordering. Automatic differentiation and optimization. So in gradient-based learning, zero gradients must lead to zero updates, as shown below. This underlies the whole convergence concept in optimization. So yeah, for the class, this is good for this scope, and support the channel. We really want to have people understand the mathematics behind it, and for anybody who wants to take it a bit further, this is usually helpful to build your intuitive thinking. I'm selling a great PDF book based off of the Axler book. So it's just simple and summarized with each example, and we're selling it on Gumroad. Feel free to check it out and support. Don't forget to like, subscribe, and comment. Thank you. See you in the next one.